Could say, though, that the gold hasn't actually vanished, and it's just in a water-soluble form called chloroauric acid. It's actually very easy to get the gold back, and I'll show you how to do that in a minute. What I have here...
Wasabi plant, as green in the soil. Most of the green wasabi paste emits in Japanese resins action, mustard and water emissions mixed up with artificial sweetness. Wasabi is not easy to grow though. It needs a supply of fast-flowing water that's exactly the right temperature and has exactly the right pH level. And once I'd found a stream that fitted the bill, I had to build a bed, which meant I needed a machine. Single-cylinder engine, 0.16 litres, top speed, 3. I'm going to call it the James May. I've now planted about 100 wasabi plants. If they all survive, that's, well, £5,000 for the roots and then another 1,000 for the leaves, probably. And that is more than you'll get from, well, hundreds of acres of wheat. This is where the money is. Wasabi plant, as
This person is trying to scoop up some seafood sauce.
Let's see how Italians make their olive oil.
The olives arrive. South African side.
32 degrees Celsius, then lactic acid bacteria run it. This creates a curd that sinks to the bottom. And now the cheesemaker carefully gathers it using a linen cloth. To make it easier, she holds the cloth with her teeth. Then she twists it to squeeze out excess moisture. Next, the curd is shaped and pressed. After that, the cheese is salted and left to mature for 8 weeks, until the moment you get to enjoy its mild, creamy, slightly nutty flavor with a hint of tang. Would you like to try it? This is how.
World's leading light bulb. Philips, International General Electric, Tokyo Electric, Osram from Germany, and the UK's Associated Electric, among others. They formed what became known as the Phoebus Cartel, named after Phoebus, the Greek god of light. There, all these companies agreed to work together to help each other by controlling the world's supply of light bulbs. In the early days of the electrical industry, there had been lots of different small light bulb manufacturers, but by now, they had largely been consolidated into these big corporations, each dominant in a particular part of the world. The biggest threat they all faced was from longer-lasting light bulbs. For example, in 1923, Osram sold 63 million light bulbs, but the following year, they sold only 28 million. Light bulbs were lasting too long, eating into sales. So all the companies in the cartel agreed to reduce the lifespan of their bulbs to 1,000 hours, cutting the existing average almost in half. To enforce the 1,000-hour limit, each of the manufacturers had to send in sample bulbs from their factory, and they were tested on big test stands like this one. If a bulb lasted significantly longer than 1,000 hours, well, then the company was fined. And there are records of these fines being issued to companies. In Geneva, here's a question. How do you steer something moving at more than 99.99% the speed of light? So
Yep, that plan's done.
It said that a criminal once...
Hello.
What are you doing here?
I got called to the principal's office.
So did I.
Not that I'm aware of. Did you? Maybe it's good news.
Never been golfing that close.
Never.
You know what you do? By the way, son, got PSA heaters on back. Show got a perfect score. Thanks, Tom. Be sure to put that up on the grid. I don't understand. Joe's the only kid in the school to ever do this. His age may be the whole country.
It was fun. I enjoyed it.
So was he. It means he pitched a perfect game, George. I've already got calls from colleges who want to be in it. Scholarship and stuff for everything. Hey, buddy. Bye, baby.
When was the last time you washed your hands?
Come on.
How long?
This is the way to go.
You'll be amazed by the result. I've always wanted to be amazed by the. What makes you think you're qualified? Makes the eggs do it. Make the. What makes you qualified for this job? I do. What?
Great, which you then try to eat by placing your amp. Number 4 is this themed chess set where all the pieces are different types of sushi. And when you're done playing, all the pieces go inside of a bento box storage case to make sure you don't lose them. Number 3 is another chess set where all the pieces are different types of mushrooms, and the board is actually a log that unrolls. But if you don't like chess, you can use the import cap where you double in checkers pieces. And when you're done playing, you can put them inside of the log and be on your way. Number 2 is a waffle game for your first, where you take. So I tried the viral ear cleaning. Everyone in Seattle keep going. I'm at Odo Set in Redmond, Washington. What you might not know is they're actually from here. Clinic is also their headquarters. Here's how it works. Check in and you're in your place. They run you through the process and put any note that you might have. They start with a camera to check inside your ear. You get to watch it. I've actually never seen one here. I'll do the demo of the hearing search and understand. Like here. And these are the FU. They're devices. They're like giant headphones. These are revolutionizing companies. Not even how cheap. What they do is they gently irrigate that kind of ears. They let them be for inside. So is it painful? No, not at all. But I wouldn't really say it's comfortable. It's not. But you will feel cleaner afterwards. Now, my ear did turn out to be not that dirty, but that's certainly not the case. So if you want to
So let's start. This is second week for thermodynamics course problem solving session. So previous week looked at how to measure pressures, temperature, and those property which are much more relevant for thermodynamics and which can be measured. And we saw some problems on those. We'll continue to see some problems on those again today, and also something related to work and heat. So to go before starting on the problems, I'll give a recap of what is covered in this week work and heat. So basically, so in thermodynamics, you still start with the sign convention. So work and heat. So the sign convention, what we use in thermodynamics is generally related to while looking at an engine perspective, where in older days it was the main aim was to produce power. So in that aspect, so what you give in to an engine is heat, so that is positive, and what you get out, your power or work, that is positive. So heat, in terms of heat, which is going in, is positive, and coming out is negative. And work, if it is you're getting out, it's positive, and if you're giving in work, then that is negative. So that's the general sign convention which we used in thermodynamics. And in work, if you see, work is what you are uh, spending on. So if you take an example, that is friction. So uh, uh, if you take any desk, if you're sitting in a desk, if you put your hand and you try to rub it, if you put some force on the table and then rub it, you will feel there is some restriction. That's because of friction. So you have to put in much more effort. But if you just glide it through without any putting any effort, you're not doing any work there. So there is no resistance. So the work comes with that resistance. Similarly, if you whatever you see PDV or whatever, there is additional atmospheric which is putting a resistance to that. So there is always uh, something which is to be overcome. And your general definition which you will see in thermodynamics books is work is something which is translated to raising a weight. So you pulling a weight up. So that is also putting a resistance, right? You have against gravity of trying to put it up, bring it up. So all terms comes out to be there is a resistance which is coming, which you overcome. So that generally is work. And heat is, there's some energy transfer because of your temperature differences. So some temperature difference, there is always energy which is transferred between a higher temperature or lower temperature, and that is another form of energy. So that's what is heat and work, and which will you see throughout thermodynamics, how this energy is transferred, and how this energy is transformed to some from one to another, and so on. And so apart from heat, work, you can have multiple types of work, kinds of work, uh, like in electrical work. So if you have electrical energy, that is also in work. And similarly, uh, because of magnetic, and so the works can be in different forms. uh, so with that, we'll proceed to see some problems. So the first one, we have the absolute pressure inside a tank is 0.4 bar and the surrounding atmospheric pressure is 90 kilopascal. So what reading would a Borden gauge mounted in the tank wall give in kilopascal? Is the gauge is this a gauge or a vacuum reading? So what we have gauge, it means the pressure difference, and a vacuum, whether the pressure what you are reading is a vacuum. So a difference is here vacuum is also, if you see in terms of absolute pressure minus the atmospheric pressure, the difference below your atmospheric pressure, if it's lower than atmospheric pressure, and that is your vacuum. And the gauge is the difference if you calculate from the absolute pressure minus the atmospheric pressure, but that's your positive. So what will be the reading be? So you can try this out, a simple problem. So one is in bar, one is in kilopascal, so to be careful there. So 1 bar is 10 power 5 pascals or 100 kilopascal. So we have a tank, we have a gauge there, and we know that inside the tank the pressure is 40 kilopascal or 0.4 bar. That is the absolute pressure which is there, and outside this tank is your atmosphere which is at 98 kilopascal. So because Borden gauge is the gauge which shows the difference, so it will show the difference between these two. So you'll get 58 kilopascal, but that will be lower than your atmospheric pressure, since your inside pressure is lower than atmospheric pressure. So this is a vacuum reading. So next question, a tornado rips off a 100-meter square roof with a mass of 1000 kgs. So what is the minimum vacuum pressure needed to do that if we neglect the anchoring forces? So you have a house and the roof mass is 1000 kgs, and because of this tornado the roof is getting ripped up. So the area is given just 100 meter square. So what should be the minimum pressure inside the house? So what is the vacuum pressure needed? So outside, because of the tornado, your pressures has dropped. So what should be the difference in pressure for the house to be ripped apart, or roof to be? Try solving this. So you can estimate the forces, and using that force you have area, you have to try to find out the pressure difference, and that will give you the answer. You can assume atmospheric pressure to be 100 kilopascal for this case, or 1.01 bar. So see how to solve this. So first we'll estimate the force which is will be acting on the roof. So that is because of the pressure difference which will be there inside and outside. So P inside A minus P outside A. So if you consider roof, there is a pressure which is acting on the roof, and from inside there is a, because of pressure there is a force acting upwards, and assuming outside your pressure is lower. So there is a pressure difference which is because of which the roof is getting pulled out. So from the inside the force will be P inside into A, and the force which is acting on the outside of the roof is P outside into A. So which you will get is delta P into A. So that's the pressure difference into A, which is the total force which is acting on the roof. So this will be equal to the weight. So weight is mg. So mass is given, and g is 9.807. So 1000 into 9.807 divided by 100 meter square, which is the area. So that will give you 98.07 Pascal. So this is the pressure difference. So already the pressure difference is calculated. So this is the difference between the atmospheric pressure and the absolute pressure or the vacuum pressure. So this is the vacuum pressure which is required. So 98 Pascal, so over 0.098 kilopascal. So next question, we have two cylinders are connected by a piston as shown in figure. Cylinder A is used as hydraulic lift and pumped up to 500 kilopascal. The piston mass is 25 kg and there is standard gravity. What is the gas pressure in cylinder B? So this is again a simple problem. So to do a force balance again here, I'll give you a minute to solve. Just a second. I think data one, I missed the data. Area of the diameter of A piston A, the bottom portion is 0.1 meter, and for B the top portion is 0.025 meter. Or 125 mm, 100 mm and 25 mm. So here there are, if you see in the diagram, there are three portions here. So one A, the bigger piston size, where the pressure due to oil A is acting, and there is gas at B which is putting force, and also the other portion which is exposed to ambient. So there is also pressure there, the ambient pressure. So if you see there are three forces because of the three pressures and one other force because of the weight of the piston. So this all four has to be balanced. So if you write pressure at A, the force because of A, and if you see it is acting upwards, and the gas because of B is acting downwards, and the ambient pressure is also acting downwards, and the weight is also acting downwards. So if you write a force balance, so PBAB plus your weight of the piston plus P naught into the area. So that area is the area of difference here, area at A minus area at B equals the force acting upwards because of the pressure of A. So PA into area of A. So that's what you get doing a force balance. So since the diameter of A is 100 mm or 0.1 meter square, 0.1 meter, so area A is 0.00785 meter square, and similarly for 25 mm piston B diameter, area B is 0.00491 meter square. So they have found out areas. You know the pressures except at B, you know the rest of the pressures. So rearranging this equation, you get something like this. So substituting the pressures and the masses which you know. So pressure at A is known as 50 kilopascal, which is given in the question, and the mass is 25 kg, and atmospheric pressure we know, can take it as 100 kilopascal. So this comes out to be the force because of pressure at B is 2.944 kilonewton. So the pressure at B is comes out to be 5996 kilopascal, just close to 6 megapascal. So next question, the sketch shows three physical situations. Show the possible process in a PV diagram. So one, you have a piston cylinder arrangement. So there is a rest here, but the piston is at the top. And in the second case, you have similar piston cylinder arrangement, and the piston is supported by a spring. And third one, you have a piston, and there's a top rest where piston cannot move up after that. So what do you think the process can be, possible process? So assume in each case the piston is moving up. So in the first case it was initially at the rest and then it's moving up. Similarly in the B it is moving up, and even at C. So how the process will look? Try to sketch each of the cases. So we'll see how to solve this. So first case, if you see, so initially if you assume this piston is at a rest, the protrusion which is shown, it's at the rest there. So initially it has force has to be balanced to the point where your pressure force exerted by the pressure in the cylinder is equal to the piston weight. If it's more than that, the piston will start moving. So till that point your volume will remain constant, and after that it will start moving up. In the second case, if you see with the piston expanding, the force exerted on the piston by the spring increases because it is getting compressed. So, your pressure also has to linearly increase because force exerted by spring is kx. So, in that proportion your pressure in the cylinder has to also increase for the piston to move up. The third case, if you see the piston, initially it will start expanding. The only force which is acting is the atmospheric pressure. So, when it is more than that, it will start moving up, and once it reaches that rest at the top, it will move again. So, after that the volume will remain constant and the pressure may increase. So, those are the three scenarios here, and this is how it will look in a PV diagram. So, the first one, your volume will remain constant to the point where the pressure is equal to the weight and the atmospheric pressure which is acting on the piston. So, if it has reached that point, and then it will start moving. At that point your pressure will remain constant, because at each cases your it is balanced by the weight and the atmospheric pressure. So, all the forces and this thing are balanced, so your pressure will remain constant. The second case, as I told, your spring force increases linearly because it gets compressed. So, your pressure will also increase linearly with volume. So, this is how it will look in the second case. The third case, if you see, so initially the pressure will remain constant. So, because the forces are balanced and your piston will be moving, and so it will increase to a point, the volume will increase till it reaches that rest. After that now it cannot move, so your volume will remain constant and your pressure will start rising. So, this is how the three scenarios will look. Do you have any doubt in this? In case 1, how the volume increases after the pressure remains same. See, so you if you see at the rest after you are heating that system. So, it will at each point assume you are slightly lower than the piston is slightly lower. Even at that point, for the piston should be at equilibrium, it has to be balanced by the pressure exerted by the gas, the pressure acting because of the atmosphere, and the weight. So, at every point above the rest, this is the three forces which are acting on the piston. So, all three will be same at every point. So, what happens is because of the heat, it will try to rise in actual scenario. So, and it will come to that equilibrium. So, the pressure will not change. So, at any point if you see both the pressure acting on the piston is always balanced. So, this pressure exerted by the gases cannot be different. So, the only way it can accommodate whatever energy it is receiving is by increasing the volume. Is it clear? Okay. So, I will move to next question. So, the air drag force on a car is 0.225 A rho v square. Assume air at 290 Kelvin, 100 kilopascal, and a car frontal area of 4 meter square, driving at 90 kilometer per hour. How much energy is spent to overcome this? So, again this is like estimating the work which has to be done. So, the air drag force is just like friction which is acting on the car. So, that is given by this expression here, 0.225 A rho v square, and v is the velocity and rho is the density. So they have given the air pressures, temperature is given, and the frontal area is given 4 meter square, and the velocity in which the car is being driven is given as 90 kilometer per hour. So how much energy has to be spent for this? So normally how do you write work? So the normal expanding case, you write it as P delta V in the piston cylinder arrangement and so on. You have seen integrating P dx, P dV, and writing as the P into change in volume. So volume, if you write in terms of area into length, it becomes a force into length, the displacement. So similarly here, work done will be the force into the length travelled or so. So the air drag force is given, force is given, so that is known, and I think x is missing. So assuming it has driven for 4.5 kilometers, so how much work has to be spent? So for this, now we need to estimate the density. We know velocity, we need to find out density to estimate what is the drag force which is acting on the car. And for estimating density, what do we know? We know pressure and temperature. So air, we can assume it to be an ideal gas. So this is how we'll solve. So density or is equals to 1 by the specific volume. So assuming air as an ideal gas, we get PV is nRT or MRT. You have to be careful which R you are using. So rho is P by RT. So you'll get P is 100 divided by 0.287 for air into T is 290, which is given. From that we can estimate density. Density comes out to be 1.2015 kg per meter cube, and the velocity is given as 90 kilometer per hour. So 90 into can do 5 by 18 or 1000 by 3600, we get 25 meter per second. So now you know rho and density, we can estimate force. So force is 0.225 A into rho v square, and maybe the question was to be driven for half an hour. Maybe I'll rewrite the question again while uploading. So delta x is v into delta t. So v we know 25 meters per second. So delta t is 30 minutes. So 30 into 60, we get 4500 meters. So that is what has been driven. The car is driven assuming constant velocity of 90 kilometer per hour. So for half an hour, it will give you 45,000 meters. So force is 0.225 rho a v square. So a is given 4 meter square, rho we have calculated 1.2015, and v is 25 meters per second. So 25 square, we get forces 676 Newton. So from there we can find out work. So work will be force into the length, or for F delta x, which will come out to be 676 into 45,000. So that comes out to be 30.42 megajoules. So that is the amount of energy or work which has been spent. So any doubt in this? Okay. So moving on. We have a 400-liter tank A, see the figure below, contains argon gas at 250 kilopascal and 30 degrees Celsius. So cylinder B having a frictionless piston of such mass that a pressure of 150 kilopascal will float it. So it has a weight such that applying 150 kilopascal we can lift the piston. So that's what is given. And the argon contained is in a 400-liter tank, and pressure and temperature is given. So the valve is opened and argon flows into B and eventually reaches a uniform state of 150 kilopascal and 30 degrees Celsius throughout. So what is the work done by the argon? So this is the process. So if you see, this is similar to what we saw in the first sketching problems. So initially the pressure here is more than the pressure required to lift the piston. The piston requires just 150 kilopascal. So it will reach equilibrium when the pressure exerted by argon, or the because you are opening the valve, now the argon will try to flow and it will lift the piston, and because you are expanding, your volume is increasing and your temperature is same, so your pressure will reduce. So ideal gas PV equals to MRT, or so if your M, R and T are constant, so PV is constant in this case. So if your temperature is constant, then with pressure, your volume will of the with increase in volume, your pressure of the argon will go down. So at it will reach a state where it is reduced from 250 kilopascal to 150 kilopascal. So there the piston will come to a equilibrium and it will not move. So it has performed some work in the process because of argon. So if you see in the piston, as I started with the class, so the work is the resistive force which is acting. So in the piston there are two. One is because of the weight of the piston, and the second is the atmospheric pressure which is acting on the piston. So these two are the which is trying to resist the piston. So you are doing work to overcome this. So that is the work which is required. So the other way is to calculate from the forces which is acting on the piston, the atmospheric pressure and the weight. Using those you can estimate what is the work done. The other way is to can also calculate using the argon, but you need to know how the process is happening, how the pressure and volumes are changing throughout the process, because you know initially this is at rest before the valve was open, and the instant the valve was open you are subjecting it to 250 kilopascal and the piston starts moving. So if you can trace out each of the states the piston is going until it reaches the rest, then you can use that data or the process to estimate the work. So that is one way of doing. The other way of doing is estimating what is the resistance which is overcome by the piston. So that is the other way of two ways of estimating the work done. So if you see, assume the system, total system as a control volume, both the argon tank and the piston cylinder arrangement, the both of this as a control volume, there is no net work which is going out of the system. In that case, that's what one of your lemma can say. So your total net work will be always 0. So the work done by the argon and the work done on the piston both will try to balance. So here you can, as I said, you need to know the final state to estimate the volume, and based on that you can find out the pressure. So PA1 VA1 equals MAR PA1, and which is true for the second state because we know the temperature. So P2 VA plus VB2. So VA is the tank volume and B is how much volume is traced by the piston. So P2 into VA plus VB2. So this is what it comes out to be, PV equals constant for this case. So VB is PA1 by P2. So this we are rearranging to find out VB2 because we know the volume A. So rearranging, this is what we get, PA1 by P2 VA minus VA. So substituting the values, we know PA1 initially it is subjected to 250 kilopascal, and the final state of the argon is in 150. So 250 into 0.4 divided by 150 minus 0.4, which comes out to be 0.2667 meter cube. So the P external force which is required, which is acting, so indirectly what we are doing is without finding out the mass of the piston, we are, because the piston will move at 150 kilopascal, so that is the resistance which is acting on the piston. So P naught plus the piston weight is 150 kilopascal. So P external into VB minus V2, VB1. So we get 150 into 0.2667 minus 0. So it comes out to be 40 kilojoules. Is this clear? So what we did is, based on the data, we estimated the volumes, the initial and final volumes, and we didn't care about how the process is happening of the argon. So, and using those change in volume, we then used the external force which is acting on the piston, which is the resistive force which is acting on the piston, to estimate the work done of the system. Okay, I assume there is no doubt in this. So I'll move to the next question. Here, 0.15 meter diameter pulley turns a belt rotating the drive shaft of a power plant pump. The torque applied by the belt on the pulley is 200 Newton meter and the power transmitted is 7 kilowatt. So determine the net force applied by the belt on the pulley in kilonewton and the rotational speed of the drive shaft in RPM. So it's another form of work which we have to estimate. So what is given is, you have a power plant pump which is used to pump water and so on. So it is connected through a pulley. It's driven by a pulley and which is of a 0.15 meter diameter. So the torque applied to this pulley is by a belt, and which is the torque is given as 200 Newton meter. They say the power transmitted is 7 kilowatts because of this torque. So we need to find out the net force applied by the belt on the pulley in kilonewton and the rotational speed of the drive shaft. So this is how the process looks. So you have a pulley, you have a belt, and there is a force which is happening. So because it's driving, the force, there is a force difference because of which this will rotate. So the net force is what we have to find out acting on the pulley to rotate it. So the diameter is given as 0.515 meter and the torque is 200 Newton meter, and the work which is transferred by the pulley is 7 kilowatt. So with this, we know torque is force into the radius here. So force into diameter by 2, so that is the torque, which is equal to 200 Newton meter. So from this we can find out the force. So force is 2 times torque divided by diameter. So it comes out to be 2.6 kilonewton. Then so and then power transmitted, power is your torque into omega. So with which you can find out the rotational speed. So we know the shaft power and we also know torque. You can estimate omega. So omega is 2 pi n by 60. So using that we can estimate n. So omega is again now power divided by torque into 60 divided by 2 pi. So that's what we'll get. So omega is comes out to be 334.2 rpm. So it's just a simple problem on the torque and so on. So next question is on thermistor. So a temperature measurement basically. So you have a relation between resistance and temperature T for a thermistor closely, which follows R equals R naught exponential beta into 1 by T minus 1 by T naught. So where R naught is the resistance in ohms and measured at temperature T naught, and beta is a material constant with units of K. For a particular thermistor R naught, 2.2 ohms at T naught is 310 Kelvin. So from a calibration test, it is found that R is 0.31 at 422 Kelvin. Determine the value of beta for thermistor and make a plot of resistance versus temperature. So I think it's a simple problem. I can try this. I'll give you a minute. Try. So if you see this is the expression. So R is R naught exponential beta into 1 by T minus 1 by T naught. So can other way write it as R by R naught, ln R by R naught, which gives you B. We can write it in terms of beta. So beta comes out to be ln R by R naught divided by 1 by T minus 1 by T naught. So you know two points basically, R naught at T naught and R at another T. Can substitute these values here. So that will give you beta straight away. It will be 2288.9 Kelvin. And so this how it will look. So R naught is at initially at 310 at 2.2 ohms, and this how the profile, because it's an exponential, so there is exponential reduction in the resistance value. So this is how the plot for resistance versus temperature looks for a thermistor. And so there's something called as sensitivity. So if you see, how do you say which is at which point it is good to measure use thermistor? What do you think, where is it good to use thermistor along this curve? So if you see, there's something called if you see common, you change for a small change in temperature, the change in resistance is good at this point. So it is better to use thermistors at this ranges compared to here. So it has more sensitivity here compared to here, because the slope is the sensitivity. So this is better here compared to at higher temperatures. So moving on to next question. So a fan forces air over a computer circuit board with surface area of 70 centimeter square to avoid overheating. The air temperature is 300 Kelvin while the circuit board surface temperature is 340 Kelvin. I think I have not given table. Using data, determine the largest and smallest heat transfer rate in watt that might be encountered for this forced convection. So basically heat transfer coefficient is given. So using that we have to find out what could be the largest and smallest heat transfer rates. So we have, this is a circuit board and you have a fan here. So this is like similar what you can see in your computers. So if you see you have your chips inside and you have a fan sitting above it to cool the chip. So it's kind of similar arrangement here. You have a chip or a circuit board and it has to be cooled by a fan, and the outside temperature is 300 Kelvin and your circuit board temperature is 340 Kelvin, and the area of the circuit board is 70 centimeter square, and you estimate what is the heat transfer with what is the smallest and largest heat transfer because of forced convection. So it is given the smallest heat transfer coefficient which you can have is 25 watt per meter square Kelvin and largest is 250 watt per meter square Kelvin. So the simple Newton's law of cooling, HA delta T, which you use. So 250 is the largest heat transfer coefficient into area is given as 70 centimeter square into 10 power minus 2 to convert it into meter, sorry 10 power minus 4 to convert it into meter into the temperature difference, which is 40, so 340 minus 300, so it comes out to be 70 watts. And similarly the smallest is heat transfer coefficient 25, so this factor of 10, so yes, smallest is 7 watts. Okay. Moving on to next question. So our air is contained in a vertical piston cylinder assembly such that the piston is in static equilibrium. The atmosphere exerts a pressure of 101 kilopascal on top of the 0.5 meter diameter piston. The gauge pressure of the air inside the cylinder is 1.2 kilopascal. The local acceleration of gravity is g is 9.81 meter per second square. Subsequently, a weight is placed on top of the piston, causing the piston to fall until reaching a new static equilibrium position. At this position, the gauge pressure of the air inside the cylinder is 2.8 kilopascal. Determine mass of the piston in kg and mass of the added weight in kg. So you have to find out both the piston mass and the weight, mass of the weight. So we know the initial pressure and the final pressure is all given. So it's again a simple problem of balancing the forces. Try this problem. I'll give you 2-3 minutes to solve. Simple problem here. See the solution. So similar problems we have encountered in the previous question. So try this out. We'll see how to solve this here. So basically there are two cases. The first case, you take a piston, you have force because of the weight and the atmospheric pressure, which is balanced by the air inside. So that's the first set of equation which you have to solve to find out the piston weight. And second set, after finding the piston weight, again balance the forces because of the weight, the piston and the atmospheric pressure with the pressure inside. That will give you the second equation. So we'll have two unknowns and you can solve two or do one after another. So the first case, we have piston, the force acting is the piston weight and the atmospheric pressure just be balanced by the air inside, pressure inside. So P air into A piston minus P atmospheric pressure into the area of the piston minus the weight P piston into G. So that is the first equation which you will get. So from here we can find out the mass of the piston. So delta P into area divided by G. So the trick part was here is given as the gauge pressure here So it's already estimated the pressure difference between the atmosphere and the air. So this is 1.2 kilopascal gauge. If you do an absolute, you have to subtract P air minus P atmosphere. But since this is gauge, so P air minus P atmosphere is what the gauge is being reading. So that is 1.2 kilopascal. So you have to be careful here. So not put it at 0.2 kilopascal. So 1.2 kilopascal into 0.5 meter square divided by 9.81, and converting it to pascals and so on, you get mass of piston is 61.2 kgs. So that we will get mass of piston. Similarly, for the second case, now instead of just piston, we have additionally weight. So that will also put some weight. So the same equation, now additional term minus m weight into g. So again dividing by g, we get m weight as rearrange. This is what we get. So P air minus P atmosphere is given as 2.8, in this case 2.8 kilopascal. So 2.8 into area of piston divided by g minus mass of piston. So mass of weight will comes out to be 81.5 kg. Okay. So I hope there is no doubt in this question. So moving on to next question. A piston cylinder device contains 0.05 meter cube of gas initially at 200 kilopascal. At this state, a linear spring that has a spring constant of 150 kilonewton per meter is touching the piston but exerting no force on it. So now heat is transferred to the gas, causing the piston to rise and to compress the spring until the volume inside the cylinder doubles. So the cross sectional area of the piston is 0.25 meter square. Determine A, the final pressure inside the cylinder, B, the total work done by the gas, and C, the fraction of this work done against the spring to compress it. So let's break down the question. So this is similar to what we saw in the first case, which we saw the PV plot. So same case. So the piston, you are applying some heat, because of which you are transferring some energy. So piston will start moving. So it will start compressing the piston spring. So we have already seen why it goes linearly, why the pressure varies linearly. So we have a linear process from state 1 to 2. And now what is being given is, initially the volume occupied is 0.05 meter cube and the pressure at that time is 200 kilopascal, and the area of piston is also given 0.25 meter square, and spring constant is also given 150 kilonewton per meter. Now what we need to find out is what will be the final pressure. So we are applying heat, the piston expands, what will be the final volume, so final pressure, and then the total work done by the gas. So what is the total work which is being done, and what is the fraction of that work is spent in compressing the spring. So we see there are two kinds of forces which is acting on the piston. One is the spring force and another is the atmospheric pressure. So the whatever work is done by the gas, it is in overcoming these two forces which is acting on the piston. So some part of work is done to overcome the atmospheric pressure which is acting on the piston, and some amount is done in overcoming the compression of the spring. So we need to find out what is the fraction of that is done to compress the spring. So that is the questions which has been asked. So how will you solve this? So try attempting this. So the process is already given. We say how it's varying linearly, and they have also said that the volume is double at the final state. So okay, I'll see how to solve this. So what is given is the volume at the end is double the initial volume. So your final volume is 0.1 meter cube. So initial volume was 0.05 meter cube. So the final volume becomes 0.1. So with this we know what is the volume which has been expanded. So initially it was at 0.5 and the piston moves, so it has expanded by some volume. So that volume is 0.05 meter cube, and since we know the area, so we can estimate how much the piston has moved vertically. That will be equal to area into the length moved by the piston is equal to the volume expanded. So we can find out how much length the piston has moved vertically up. That will give you how much the spring has been compressed. So x is delta V by A. So delta V is 0.05 meter cube divided by area, which is 0.25 meter cube. That comes out to be 0.2 meter. So the spring has been compressed by 0.2 meters. So now the force applied is Kx, we know, for F is Kx for spring. So K is 150 kilonewton per meter, the spring constant, into the compression, which is 0.2 meter. So whatever the piston has moved vertically, that amount of compression is happening on the spring. So that comes out to be 30 kilonewton. So additional pressure applied by the spring on the gas at this state is F by A. So 30 kilonewton divided by 0.25, which comes out to be 120 kilopascal. So what we basically did is at the initially when the piston is not compressed, it is at some pressure, and whatever it is balanced by the atmospheric pressure. So once the piston expands and moves vertically, at that final equilibrium state, you have three forces. One is the gas pressure and atmospheric pressure, which will be the atmospheric pressure is not changing. So whatever increase in pressure is because of the spring pressure. So we are estimating what is the pressure because of the spring compression. So that is the delta P with which the pressure has increased. So that's what has been done here. P is F by A. So 30 kilonewton by 0.25. So which is 120 kilopascal. So or this much amount of pressure has to be given for the spring has to be compressed by 0.2 meters. So that's the other way of looking at it. So the total pressure, the final pressure of the gas will be the initial 200 plus 120, so which comes out to be 320 kilopascal. So this is how now the system will look like. Initially it is at 200 and linearly varies to 320 kilopascal, and the volume is by that time has doubled from 0.05 to 0.1. So we have found out the first, what is the final pressure. The second is to estimate the total work which has been done. So the easy way of finding is to find the area under the curve. So we have already drawn how the process will look, and we can just easily calculate the area. So area is 200 plus 320 by 2 into 0.1 minus 0.05 meter cube. So that comes out to be 13 kilojoules. So this is total area, or you can find it in two parts, the area of the rectangle and the area of the triangle. So that's the other way. So it comes out to be 13 kilojoules. So If you see, the third part of the question was to find out what is the work done by the spring, done in overcoming for compressing the spring. So the fraction of the work done against the spring. So to compress it, that's the third part of the question. So if you see, the work done in overcoming the atmospheric pressure remains constant. So that is the atmospheric pressure into the delta V. So if you see, that is represented by the green portion here, 1, which is denoted by 1. So that is the work done in overcoming the atmospheric pressure. And the second, the triangular portion, is the work required for compressing the spring, or the work done against the spring. So that is represented by this gray portion and denoted by 2. So that is the fraction of the work which is required for the spring. So you can estimate by just the triangle or the other, subtracting the rectangle from the total work. So that comes out to be, spring work is half into 320 minus 200 into 0.05, comes out to be 3 kilojoules. So what we did is the PV delta V in the W spring, to find out the area. So the other way of finding out is the simple physics what we have seen is half kx square. So that comes again will comes out to be 3 kilojoules. So both will be same. It will not be any different. So we see the total area work done by the gas is 13 kilojoules for the total area, and the piston, the atmospheric pressure which is acting, so that is 10 kilojoules, and the spring work done is 3 kilojoules. So if we sum it up, the air system, it is giving out work, so that is will be positive, the other will be negative, the sum will be 0. So that is why the net will become 0. If you take the system plus surrounding, the surrounding is your spring and the atmosphere which is receiving that work. So the net work becomes 0. So the gas is 13 kilojoule. Any doubt in this question? Okay, so we move on to the next. Next question is, air is contained within a vertical piston cylinder assembly is shown in the below figure. On its top, the 10 kg piston is attached to a spring and exposed to an atmospheric pressure of 1 bar. Initially, the bottom of the piston is at x equal to 0 and the spring exerts a negligible force on the piston. The valve is opened and the air enters the cylinder from the supply line, causing the volume of the air within the cylinder to increase by 3.9 into 10 power minus 4 meter cube. The force exerted by the spring as the air expands within the cylinder varies linearly with x. So is given by F spring is kx, where k is 10,000 Newton per meter. The piston phase area is 7.8 in 10 power minus 3 meter square. So ignoring the friction between the piston and the cylinder wall, determine the pressure of the air within the cylinder in bar when the piston is in its initial position. Repeat when the piston is in its final position. The local acceleration of gravity is 9.81 meter per second square. So before showing the solution, at least I want you to at least try out or figure out how you will solve this question. So in a sense, it's similar to what we saw previously. Just think over the question. I'll give you a minute or two. So okay, so we'll see how to solve this problem. So let's say what is known. So we know G is 9.81, K is 10,000 Newton per meter or 10 kilonewton per meter. In the piston, we know area is 7.8 into 10 power minus 3 meter cube, and the mass is 10 kg, and the volume expanded, the change in volume is 3.9 into 10 power minus 4 meter cube. So this is what is known to us. So the initial case, the initial to find out the initial pressure, that's what we asked. To find out the initial during the initial position when the spring force is 0, we need to find out the pressure and the final pressure. So initially, so if you say piston, this can be the force which is acting, the spring force, atmospheric pressure from the top, the air pressure and the piston weight. So initially the spring force will be 0 at x equal to 0, and then at that point if you calculate the net force, so the pressure because of the gas into area equals the atmospheric pressure into area plus the piston weight. So with that we can estimate the pressure. So the atmospheric pressure is 1 bar and mass is given as 10 kg into G 9.81 divided by area, which is 7.8 into 10 power minus 3, and divide by 10 power 5 to convert it into bar. So this comes out to be 1.126 bar. So that is the initial pressure within the cylinder. So next is the final pressure. So the spring force, atmospheric pressure, and this air pressure and the piston weight here, all 4 are present. So this is how the expression will look now. So P2 is the second state, P2A into P atmosphere into A plus the piston weight plus the spring force. With this we can find out P2. To estimate the spring force, we need to find out the compression of the spring. So again the compression of the spring is calculated using the change in the volume divided by area. So change in volume is 3.9 into 10 power minus 4 meter cube divided by area 7.8 into 10 power minus 3 meter square. So that gives you excess 0.05 meter. So substituting for x in F spring, we can estimate the force. So P atmosphere is known 1 bar, mg by A is known. So we can straight away use P1 here, P atmosphere plus mg by A, we can use straight away P1, and the delta P because of this compression spring. So 1.126 bar plus 0.641 bar comes out to be 1.767 bar. So I hope any doubts till now, or any doubts in general before going to next question. If you have any doubts, you can ask. Okay, so next question. So nitrogen gas with a piston cylinder assembly undergoes a process from P1 of 20 bar and V1 of 0.5 meter cube to a state where V2 is 2.75 meter cube. The relation between pressure and volume during the process is PV raised to power 1.35 equals constant. For the N2, determine A, the pressure at state 2 in bar, and B, the work in kilojoule. So the nitrogen is going through a process. So here the process is given how the nitrogen is going through between the states 1 and 2. So it is following a path PV equals 1 raised to power 1.35 equals constant. So that is the process line if you draw in a PV curve. So that's how the individual states are along the process from state 1 to state 2. So P1 is given and V1 is given and V2 is given. So we can straight away estimate pressure at state 2. So PV raised to power 1.35. So P1 V1 raised to power 1.35 equals P2 V2 raised to power 1.35. So we know 3, we have to estimate, the only unknown will be P2, which we can straight away find out. The second is to find out the work. So that we'll use a integration. So we'll see how to solve this. So as I said, P1 V1 raised to power n equals P2 V2 raised to power n. So we can find out P2, n is 1.35 in this case. So P2 will come out to be, P1 is 20 bar, so 20 into V1 by V2, it's 0.5 by 2.75. So the raised to power 1.35, it comes out to be 2 bar. So if you see, the volume is expanding, so volume is increasing, so your pressure has come down from 20 bar to 22 bar. So if you plot in a PV curve, it will be like an exponential curve which we saw for the thermistor. It's kind of that, or a power curve you can say. So the other is to find out the work done for this process. So that is integration of P dV. So we can estimate this expression. It will come out to be, you can put P as C by Vn and then integrate it, and you will get in terms of C and V and N, and you can replace C as again PV raised to power n, then end up with this expression here, P2 V2 minus P1 V1 divided by 1 minus n. So here now we know all the values. So substituting the values, P2 is 2 bar and V2 is 2.75 and minus P1 is 20 and V1 is 0.5 divided by 1 minus 1.35, multiply by 10 power 5 because the pressures are in bar, and divide by 10 power 3 to convert into kilojoules. So it comes out to be 1285.7 kilojoules. Any doubt in this question? So any doubts? Okay, if not, I'll move to next question. So I have a gas in a piston cylinder assembly which undergoes an expansion process for which the relationship between pressure and volume is given by PV raised to power n is constant. So the initial pressure is given 3 bar, the initial volume is given as 0.1 meter cube, the final volume is given as 0.2 meter cube. So we need to find out the process work for 3 different processes. One is n is 1.5, the second is 1, and in a third case n is 0. So if we put PV raised to power 1.5, similar to what we did in the previous problem, and second is PV equals to 1, n is 1, so PV equals constant. So this will turn out to be in the future classes we will see, it will be, turns out to be a isothermal process. And n equals 0, so if you put n is 0, anything raised to power 0 is 1, so it becomes P is constant. So if you see, plot it in a PV diagram, so this is how it will look. The A part 2A PV raised to power 1.5 is the bottommost curve, so 1 to 2A, so that is the curve how it looks for PV raised to power 1.5, and if you put PV equals constant and it goes slightly up the curve, it becomes this are shown in P 1 to 2B, and the third is your pressure is constant, so that's just a horizontal line from 1 to 2. So in each of this process you see the state points are different. So we need to find out the area of under the curve for each of these 3 curves to find out the net work which is generated in the process. So initial pressure is given as 3 bar and the initial volume is given as 0.1 meter cube, and we know the final volume which is 0.2 meter cube, but the final pressures will be different in each of the cases. So the third case, because pressure is constant, your pressure at the end will also be same, but the others will not be. So In the first case, you can use straight away the same formula which was used in the previous problem. So W is P1 P2 V2 minus P1 V1 by 1 minus n. So it will come out to be that. So just shown what I explained verbally. So your work done, which is integration of P dV. So P you can write this as constant divided by V raised to power n in times dV. So when you are integrating it, it becomes constant, just a constant into V raised to power 1 minus n by 1 minus n from state 1 to 2 or V1 to V2. So substituting that, we get constant V2 raised to power 1 minus n minus constant V1 raised to power 1 minus n divided by 1 minus n. So this becomes P2 V2 minus P1 V1 divided by 1 minus n. So that's what we get. So work, we can substitute the pressures and n. So the only unknown here is the final pressure P2 when n is 1.5. So the similar way what we did. So P2 is 1.06 bar, and substituting there we get work done as 17.6 kilojoules. The second is for n equals 1, we perform the same thing again. So integration of P dV. So substituting P as constant by V, we will get integration of dV by V, the constant is outside. So 1 by V is integration is log ln of V. So ln of V from state 1 to 2 will give you ln V2 by V1, and constant is PV. So you can either use the initial state or the final state. So here we are in terms of initial state because we know both pressure and volume at the initial state, or you can, if you know, you can estimate the final pressure as well. So you can write P1 V1 equals P2 V2. You can find out the pressure at the final state. So here P1 V1 ln V2 by V1 is what we get for work done. So this comes out to be, substituting P1 is 3 bar, V1 is 0.1 meter cube, converting into bar and converting the whole thing into kilojoules, and ln V2 is 0.2 and V1 is 0.1, which is given. So it comes out to be 20.79 kilojoule. So that is the work for this process. And if you see for third process, when n is 0, straight away P delta V. So integration of P dV, P is constant, so we can take it out. So it becomes delta V. So P delta V. So pressure is 3 bar and V is 0.2 minus 0.1, which is 0.1, multiplied by 10 power 5 divided by 10 power 3, which will give you 30 kilojoules. So that is the work done for the third case. So the simple problem on estimating work for different process. So any question in this? If not, I think I have last one problem for today. Let's see, and we can end the session for today. Or if you have any doubts, you can ask on that. So this just what we did previous problem is just you have two sets of process happening, and initially you are at state 1 here and 100 kilopascal and volume of 0.07 meter cube, and it goes to linearly to state 2 which is at pressure of 150 kilopascal and volume of 0.055, and from 2 it is going to state 3, again the pressure is constant in this case here, to a volume of 0.015 meter cube. So that's the two processes which is happening. So we need to find out the total work. So this is just a combination of what we did previously. The simplest case, here you don't have to integrate anything. It's a linear variation from 1 to 2 and then a constant. So it is just, we can straight away calculate the area under the curve because we know the values, coordinates of each state points. So for 1 to 2 process, it's just P1 plus P2 divided by 2 into the change in volume, that will give you the area. And the second case is the pressure is constant 150 and multiplied by the delta V, so that will give you the area. So that's what is written here. So P delta V comes out to be P average V2 minus V1 plus P2 V3 minus V2. So this is how it looks. So substituting the values, as I told, P1 is 100 kilopascal and P2 and P3 are 150 kilopascal, and the volumes is given in the x coordinate. So it comes out to be minus 1.875 kilojoule and minus 6 kilojoules. So total is minus 7.875 kilojoules. So why negative? So since you are compressing from 0.07, your volume is decreasing, see 0.07 to 0.005, and your pressure is increasing. So it's just like you are increasing pressure, so you have to do work to either compress or increasing the pressure. It's just like you're filling in air in your cycle tubes or whatever. So there you're doing work, right? You're compressing and you're pressurizing whatever, you're pumping in fluid to the tire, so just and increasing the pressure inside the tire. So so you are doing work. So the same scenario. So you have pressurizing and you compressing the volume, and similarly in the second case also. So your pressure is constant, but still your volume is decreasing. So either both the cases you are performing work on the system, that's why it's negative. So minus 7.875 kilojoules. So I hope this is clear. If you have any doubts, I'll clear on those, or I have finished what the questions I have prepared for today. If you have any doubts, we can discuss, or we'll meet you on next Tuesday, where we'll look at some more problems on work and heat, and also look at the first law of thermodynamics. So if there is no questions, we can end the session. Thank you for joining. See you next week on Tuesday, same time at 6. Thank you. I just ended the session now. I finished what I've prepared for today. If you have any doubts, I'll be happy to help or clear those doubts. If you have any doubts on the previous week's lectures or something, you can ask those, or I can end the session and see you next week. we have no doubts, I'll close the session. Thank you for joining. See you next week.